Multivariable calculus. This is Miss Deer, your favorite and only calculus teacher, back here on the mic. We are going to extend, so we extended the divergence flux form of Green's theorem into Gauss's theorem or divergence theorem. So we're going to convert today the curl theorem into Stokes' theorem. And we turned a double integral into a triple integral. Now we're going to turn a line integral into a double integral. So let's start with writing Stokes' theorem. And so instead of a closed region, we're now going to have an orientable surface. So we want to start with S, and it's going to be an orientable surface with unit normal vectors on it, bounded by a simple closed curve. And we're going to orient this curve moving in the positive direction. So if the piece of paper that I'm writing on is my orientable surface, then the boundary around the piece of paper would be my orientable curve. So we say that if F, now this is our vector field, and it has to be differentiable on an open region. And this region now has to include S, which is our surface, and C, containing S and C. Then the line integral of the work done around the region is equal to the accumulation over the surface of curl F accumulated across the normal vector. Now remember that the normal vector is, remember we have the partial derivatives over the magnitude of the partial derivatives. So that denominator here is going to cancel as we turn this into a dA. Remember, so this is actually going to make this a little easier to work with. So let's start by giving us an example, and we'll evaluate it both ways. So we need a vector field. So let's let f of x, y, z be negative y plus z I hat plus x minus z j hat plus x minus y k hat. So this is a differentiable vector field, and I need a surface. So my surface is z equals rad 1 minus x squared minus y squared. Now sometimes you will have a restriction and a finite end to this surface, right? But because we're looking at a hemisphere, it has a natural edge. And that natural edge occurs the smallest value that we can get, which is when z equals 0. So we're going to find this basically Stokes' theorem says that the circulation around is equal to the component of the curl over the surface area. So if I want to do it the old way, we'll call it, so I want to accumulate along this curve f dr. So this is again the accumulation, the component of the field acting on the tangent vector along the surface. So in this case, again, the boundary occurs when z equals 0. So z is going to be 0 here, z is going to be 0 here. So my accumulation along the curve of negative y plus z dx plus x minus z dy plus x minus y dz, we can see that this is going to disappear, this is going to disappear, and this is going to disappear because we're not actually changing z. So along z equals 0, along z equals 0, I'm going to write it again because I can't look over here. I get the accumulation along the curve of negative y dx plus x dy. And again, this curve is just the unit circle. So let's define c to be cosine t I hat plus sine t j hat. We're just going to plot these into here. The integral along the curve of negative y, so negative sine t dx, the derivative of cosine t is negative sine t, plus x cosine t dy. Well, sine squared plus cosine squared is 1. I want to do the full circle, so my t values go from 0 to 2 pi, and I get 2 pi.